Okay, my talk today is 3D homogeneous locator for magnetic anomalous source. Two tasks. First is algorithm development, and then testing. Okay, magnetic source means unexplored audience, like that, and the geological features include faults or mineral ore and natural resource. And this shows that one example of use linear feature associated with faults from geomagnetic analysis. If we look at this fault and magnetic shows up a linear feature. So many such features associated with the maximum magnetic. This is one example from New Mexico. Grant and Hudson did that work. Now, we look at the algorithm development for a locator. We know GPS is a locator, but if magnetic source is under the ground, how can we locate that? First, we introduce one function called homogeneous function. It's t, x, y, z of degree n. It means that if we times t, x, t, y, t, z, and then it becomes t to n, and then times the original function. This function is called homogeneous function, and it was applied in the standard Euler deconvolution. We they did that in 1990, published the result. And from this function, we can get this equation. This is a well-known Euler deconvolution equation. So this x prime, y prime, z prime are here is the source position. Now, x, y, z is the location of your measurement. You take many measurements. So I means the ice measurement. Now, solve this equation for x, y prime, x, y, z prime, and you will get the, or you solve this measurement for x, y, z prime, you can locate the source. Here, the n here is the degree n, but here we introduce the index called the instruction index is elective n. So this B is the magnetic field at this point. Okay, it's a regional. So if we look at this, this is SI equals 0, not n. SI equals 0 is magnetic contact. It's a fault. And if it's 1 associated with deep dark, and if 2 associated with pole, pole means it's a non-cylindrical or non-magnetic source at the end. So it's pole. If it is 3, it's dipole. Okay, dipole could be just to show you the audience. All right. So now we develop our algorithm based on a proposition. This is more mathematical. When a function txyz is a homogeneous function of order n, now is also negative si, which is the instruction index, of each of its derivatives with respect to xyz is also a homogeneous function, but of order n minus 1. So based on this mathematical observation, then we can obtain 3 equations. One is, look at this is x, x means the second order derivative or tensor, and xy and xz. So we need to use not only the derivative but also the tensor component. Now we have 3 equations based on this mathematical observation, and the original Euler equation, you would use just the derivative, the 3 derivative. So we form 4 equations. Now we combine these 4 equations to a single matrix equation. So this is the matrix we combine. Now big X is the location of the source. Okay, this is location. Now the red one is our task. We wanted to solve that. And the right one is also we combine the 4 equations, and this we can obtain or measure. Okay, so solve this equation, we got that x, big X, which is the 4 unknown. Then we got the location and also the index. And for this reason, we called this a different name, homogeneous locator. We do not, the difference between this algorithm and the standard order deconvolution is we do not need to use all the data, more than one data set for one single solution. I will show you that the benefit. We use more data than just magnetic measurement or gravity measurement. Okay, this the second task. I show you the testing and the synthetic data. You can use many synthetic data, but for clarity, I show you here just 5. So A, B, C, D, E. Now the AB for pole and C, D, E for dipole. So this is the location. This is the depth. This is the truth, and this is the value, and this index, you show that for this pole, 2, for the dipole, 3. Okay, dipole, many metal objects in the subsurface we can model as a dipole. Now this is the total Earth's magnetic field, and this is the magnetic north. So we know the angle between that magnetic north and the total magnetic field we call the inclination angle. And the angle between the geographic source and the magnetic source we call the declination angle. So now, if you have a dipole, you have a magnetic source, and it has its own declination angle and or inclination angle. If this angle exactly equals the Earth's angle, there is no remnant magnetization. If not, there is. Okay. All right. This shows that the magnetic anomalous and the derivative for those 5 objects. So you can see that there are A and B for the pole and C, D, E for dipole. Now this calculation, this figure, if you look at that here, it does not show clearly. So we zoom in. We look at this detail of a single object. So this is for the pole, okay, and this is magnetic anomalous. This is a magnetic derivative in X, Y, and Z. So you see that pole, yeah, you see there's a structure for pole, okay? Especially if you look at the DZ, it's just more like a circular Now we look at the dipole. If we look at this dipole, we zoom in, see this detailed structure. And this is the magnetic anomalous for a dipole. So you see clearly the feature and lower and higher. And this is the derivative of y, and a derivative of z. So now we got all this data, and then we wanted to invert the data. So we input all this data. Also, based on this, we also calculate the tensor, because we use also the full tensor gradient. And we look at the result. Okay? We look at the result and the location. Now we got it for non-remnant case, and we locate. This is the result. This first column is the result with no remnant magnetization, and the second column is with remnant magnetization. And if we compare the truth and the inverted, we got the error for x. It's about from minus 0.1 and positive 0.3 for y, and 0.2 to 0.02. And z, now look at the z, we have a larger error for the depths. But for the horizontal, it's pretty accurate. We can locate that. And with remnant, we see same type of error, but we could see a little bit larger error. That means the remnant dation is a little bit higher. So this shows the total solution, 80, 28, 29, and it's supposed to be 5, is it? So we have more solutions. This is the problem, okay? And this is the channel problem. Now, let's look at that for the stand or deconvolution. And we do the same thing. If we look at the error, okay, and we compare the error between the present algorithm, the general, the stand or the deconvolution, and look at the x error, okay? This similar, a little bit bigger, but this one is much larger than the present algorithm. And also, the solution for this algorithm, 29, and this one, 402 and 380. So now, I will show you more results. This is a big improvement. And we reduce the total number of solutions. Okay, so now second test is we use field data in the Los Angeles Valley, and we only know there is a seated UXO, and this seated O, we know the position, so we invert, and we show the result. This is the present algorithm, this is the standard order deconvolution, and this is for S equal to, SI equal to. So the solution for this one is 3,500, and this is 26,000. So our present algorithm only have about 13% of the total solution of that one. And too many solutions for this algorithm is the general problem. Now we look at that, if we use SI is 3, which means the dipole, okay, dipole. And we still got about 2,000, and this is 37,000 solution, and it's about 10%. And we look at the position of the seated UXO. This is pretty much, we can locate it accurately with about 2 solutions. But this one, about 71 solution to locate the seated UXO. All right, so we go ahead with the last testing, and we use the field data from San Luis Obispo, California. This is the site, and this is a typical site with a lot of UXO. And now this is the area for the study area, but we focus on this area. All right, so this is the area, and this is the instrument magnetic array to measure the magnetic field. This is the original magnetic field data, and there is targets. We know the targets, about 200 targets within this area, and we know the depths of the target. If you look at the depth, and this is the total. About 200 targets. Now we invert. We use our algorithm to invert for the all the data. We got about 5,000, and for the standard algorithm, if you look at the pole, then we got 45,000. We still got about 10% of the total solution. But if you look at this this box, is the location of those target. We know the target. So both algorithms locate correctly all the 200 targets. Okay? And now we look at this one, which use SI equals 3, which is dipole. And the dipole, this is our algorithm, 3,070 and 1,000, about 4.4%. And if you look at the location of this red box is the location of the target. Comparison with both this one, we still have much fewer solution. Okay, so if we look at the original data and look at the deep source, okay, look at the deep source and look at these 3 deep source. And we see that our algorithm can locate more deeper source. And in this, associated with this 3 regions, if you look at that, the dark red and red is the deeper source for the. Okay, so summarize our result. First, we developed this algorithm we called a homogeneous locator. And from the comparison of the remnant and non-remnant magnetization. The remnant magnetization generally decreases the locating accuracy, and also the tests show that we do produce much fewer solutions than the standard Euler deconvolution and give less false detection. And generally, it gives higher accuracy and in the locating. So this is the presented algorithm. But the story is not the end. How can we uniquely locate the magnetic source? As I said, we produce more solutions if we just produce 5 solutions for the 5 target and or 200, and that's the future work. And so thank you.
Thank you very much. No time for questions.